In lesson 11, we're going to look at splitting triangle sides with dilation. So we're going to investigate parallel segments within triangles. So go ahead and look at this picture and what do you notice and what do you wonder? You can pause the video and write down a few things and then come back. All right, so maybe you noticed a couple triangles. You saw a few things that could make triangles. So maybe you saw a triangle here. Maybe you also saw a triangle, a larger triangle here. Hey, maybe you noticed these two lines being marked parallel. Okay, and you also noticed off to the side that they were said to be parallel here as well. Okay, thinking that that makes a dilation because we know that dilating segments is parallel. So if we have parallel segments, thinking this is a dilation, maybe B is the center of dilation. Okay, dilating MN out to AC, we see that these kind of lines go further. Okay, they're lines versus just the segments within the triangles. So versus just here and just here. Okay, so thinking of them as infinite length versus just those segment lengths. So could have come up with some other stuff, but that's just a few things maybe you noticed. So when we're looking at this, let's look at this diagram, and we have this question that's being posed. Does a parallel line, okay, does a line parallel to one side of a triangle always create similar triangles? Okay, so if we start with a triangle, and then we have this line and it's going to be parallel to that side of the triangle, will it always create similar triangles? Okay, so wherever this parallel line ends up, will we have similar triangles? Okay, so this is kind of what it's asking. This is kind of what that looks like. And we could use this on any of the sides. So in your book, create several examples, okay, similar to this. Like here would be like if I wanted to draw it here, this would be an example, okay? Or if I wanted to put this line here, then I could make these lines solid lines here. And then that would be an example. Just marking up the lines that are parallel as well. Okay, and probably adding in like A, B, C to your triangle, and then maybe B prime, C prime, or MN or something like that. And again, this could go on any of these sides, so you don't have to keep drawing it like this one. Okay, you could, you know, extend these sides. So kind of thinking of these sides being extended. And then taking a look at this line. Okay, so taking a look at if this line was parallel, drawing some examples that way as well. So it doesn't have to just be like that. But draw yourself 3 to 5 examples in your book. And then, so pause the video, create several examples, and then come back. So you should have created several different examples of triangles. And so maybe, you know, your triangles looked something like this. So here would be one example that could have happened. Okay, maybe you did an example like this. Okay, and then this line parallel. Okay, maybe you did it way up there. But created several examples of triangles here with parallel lines. And so now trying to determine, is our conjecture true or false? So when we see that these lines are parallel, will we always have similar triangles? Okay, so decide if it's true or false. If you thought it was false, make it more specific. So seems like it's true. Okay, if you did out here, you'd have to have extended the sides of the triangle, right? So if this had been your original triangle and you moved the segment out here, you just kind of extended these sides to get parallel lines, but appears to be true. And then, so when we take a look at this, what additional information on this triangle do we know so that we can actually prove that this is true? So a hint here, if you need one, is what do we know about parallel lines and angles? So when we're taking a look at this line being parallel to this line, what do we know about angles there? So if you remember back to when we learned about parallel lines, okay, we know corresponding angles. So if we think of this as a transversal, we know corresponding angles, this one and this one are going to be congruent. Okay, if we look at CB or CN as the transversal, we also see a set of corresponding angles here. So we've got some angles in there. So does that help us prove that these two triangles are going to be congruent? So hopefully it does help you. Okay, so now write an argument that would convince a skeptic based on what we now know. Okay, so we now have some of this stuff labeled. So write an argument, okay, based on this that would help you prove to a skeptic that these two triangles are in fact similar, or that we'll always get it with parallel lines. And here's a word bank for you to use when you're writing out your proof. So pause the video, come back once you've gotten something written. Okay, so when we're taking a look at this, so let's go back and write this proof here. I'm going to actually write it on this screen. So let me get rid of this. So if we're going to write this, okay, so we know that segment MN is parallel to AC. Okay, because that's what we were talking about. That was given to us in the problem. This is what we're talking about. So angle A is congruent to angle, and then I want it to this little M, okay, but there's multiple angle M's here, so I'm going to have to name it with 3 letters. So angle A is congruent to angle BMN because they are corresponding. And angle C is congruent to angle and then BNM because they're corresponding. So maybe I don't even want to write it out. Maybe I don't want to write because they are corresponding. Let's put this all together. Okay, so we've got angle A is congruent to angle BMN and angle C is congruent to BNM because they are corresponding angles. Okay, so this is the same justification for each. Therefore, triangle ACB and triangle, so ACB and MNB are similar by angle-angle triangle similarity theorem that we learned the other day. So once you get 2 angles, so if you have parallel lines, you're always going to have those corresponding angles congruent, which then means you're always going to have 2 sets of angles, which makes the triangles similar by angle-angle. So a line parallel to one side of a triangle always creates similar triangles. So if we take this diagram, the 2 triangles that are going to be similar would be ABC. Okay, so that bigger triangle ABC and is always going to shrink down or expand onto MBN because A and M are always going to be congruent and C and N are always going to be congruent. And then B is shared in the 2 triangles. So then when we look at it, that also means then that we have this proportionality. So a parallel line to one side of the triangle divides the other two sides proportionally. Okay, so we've got this line is parallel to this side of the triangle. Okay, so these other two sides are split proportionally. Okay, meaning that when I divide the other two sides, so this side, this little chunk divided by this chunk, so AM divided by MB. So when I divide that, it's going to equal when I divide these other two chunks. So this little chunk CN divided by NB. So those little pieces are going to be proportional. So is the entire triangle. Okay, so when we're looking at the entire triangle, remember that we've got the similar sides here as well, would give us a bunch of proportions we could write. So from this thing, from the similarity statement, right, we could get AB divided by MB is equal to BC divided by BN is equal to AC divided by MN. So we also have the proportionality of the sides. Now we also have the proportionality of the chunks. This chunk divided by this one equals this divided by that. So let's take a look at these two triangles. Can we find the missing pieces? Okay, so can we find the missing side? So what are the missing sides? So all of these little segments in here, can we get all of them? And so we know that we can split these proportionally. So there's a lot of different things you can do in here. One thing to notice is this right angle. So we can find this side using Pythagorean theorem. Okay, so we can find that one using Pythagorean theorem. So we would do 3 squared plus 4 squared equals that side squared. So 9 plus 16 is equal to side AB squared. So 25 is equal to AB squared. And then we would square root both sides and we'd get 5 is equal to AB. Okay, so we know that that piece is 5. Another thing you can see is we've got this whole length over here. Okay, so we've got this whole length here is 7.5. So if the whole thing is 7.5 and this little chunk is 3, we can just subtract those. 7.5 minus 3 is 4.5 to get us this piece. That helps us because now we see that we've got this piece and this one. So we know this will be in the same ratio. Okay, so if we take and do 4.5 divided by 3, then we're going to be able to get our scale factor of 1.5. And not our scale factor, but just proportionally between these two little chunks. Okay, so then we'll do the same thing here. So we'll multiply this 4 by the 1.5 so that we can get 6 for this one. And then when you go, so now you have those chunks being proportional. And then when you start to look at now this 5, when you're trying to get to this side, this is the full side of the triangle. So you've got a couple options that you can do here. So you can just look at the sides and do Pythagorean theorem again, okay? Because we've got this side now and this side. Okay, this one was 7.5. And this full side here is 10 when we add 4 and 6 together. So you can do Pythagorean theorem that way. You can also set up proportions with the sides of the triangle. Okay, so you can look at this side of this triangle. So this littler triangle here is 4. Okay, so that one is 4. Let me get a different color because I've already got that used. Okay, let's use red. So we've got this one, whoops. So this one right here is 4 for this little triangle. okay, versus 10 for the big triangle. So if we're going to set up a proportion here with the triangles, we would have 4 versus 10. Let me get my colors right here, okay? So 4 versus 10 is going to be equal to 5 versus x, this whole, like, let's just call this x. So then we could cross multiply. So x times 4 is 4x equals 10 times 5, which is 50. Then you could divide by 4 and get x equals, what do we get here? Divide by 2 is 25. Divide by 2 is 12.5. Okay, for x. So go ahead and look at this next one. See if you can come up with some stuff there. They give you some extra lengths in the directions here. So they tell you EG, so this whole side here is 12. And EB, this little piece here, is 2.5. So they give you that right away. So you can actually get the scale factor here versus just the proportional sides because they're giving you the length in the smaller triangle. So this one is 5 versus the bigger triangle length is 15. So we know that our scale factor is 3. So if I have one of these smaller lengths, I would multiply it by 3 to get the bigger one. Or if I have a bigger one, I would divide it by 3 to get a smaller one. So in knowing that, we see this 12. So if we take the 12 divided by 3, we get 4 for this little piece here. So this little triangle length would be 4, which then we can do 12 minus 4 to get this little piece here as 8. Since that whole thing needs to equal 12, we know this is 4, so that's got to be 8. So then you've got a couple options on this next side. So you can take the 2.5 and you can multiply it by the scale factor of 3. So we can multiply this by 3 to get that whole side. And then you could subtract. Or knowing the proportionality of these pieces. So this 4 to get to this other little chunk, you multiplied by 2. So you could do the same thing here to get this little piece. So we could just multiply by 2 and get 5. And that would be the same because 3 times 2.5 is 7.5 for the whole thing. 7.5 minus 2.5 is 5. And we can see when we multiply this by 2 and get 5, 5 plus 2.5 is that 7.5. So a couple different ways to be looking at that. All right, so the main theorems in this lesson is that if you have a triangle and you have any line parallel to the base, the little triangles that are created by that, okay, the two triangles created by that are going to be similar to one another. Also, this parallel line cuts these two sides up proportionally. So not only will you have the scale factor from red to blue, you'll also have these two chunks being proportional. Okay, so these two chunks will be in the same proportion. All right, and then the lesson summary. So we've got segment FG is parallel to AC. When that happens, then we can show that the corresponding angles are congruent. This is how we proved that the two triangles were in fact similar. So parallel lines creates corresponding angles that are congruent every time. So we knew these angles would be congruent. So then we have similar triangles. And then we also got that these sides would be proportional. Okay, so this piece over this piece. So this little chunk, okay, over this little chunk is equal to this chunk over this chunk. And then the summary is just going to go in and give you some examples. So some specific examples if you knew some of the side lengths here. So if we knew some of these, they're just going to go through so you could look at drawing those on there and seeing if that makes sense. Okay, so they're saying if you knew BA, this whole thing was 9, and you knew BC was 12, and you knew that GA, this little piece here, was 6, could you, and then FC was 8. Okay, so if it's 2/3 of the way. So they gave you 2/3 here. So then 2/3 of 9 is 6, and 2/3 of 12 is 8. And then you can see that this would be 3 to total 9. This would be 4 to total 12. This is times 2, and so is this. So you can see some of those proportions happening there. So again, they're just giving you some specific examples in that paragraph. And then ultimately a segment in a triangle is parallel to one side of the triangle, it divides the other two proportionally. Okay. So this is the general statement, and this is the specifics to show you what's exactly happening.